In this video, we're going to continue our discussion of general circuits, circuits that contain resistors, capacitors, and inductors, and we're going to interpret the results we've obtained already. We're going to show that simple circuits function like what we call filters. We'll define those in just a second. We'll extend our ideas of the equivalent circuits to the case where we have impedances. That's very straightforward. And we'll also use impedances to talk about what's called complex power. It makes it very easy to do power calculations when you use complex power. Okay, so the big question is, what is this circuit doing? We can figure out its output, but let's review how we got that output for our sinusoidal input, and this will lead us to an understanding of what the circuit is really doing. So, what we did is that we assumed that the source was a sinusoid of some sort. We assumed A times a cosine 2 pi f naught t, and we wrote that as the real part. This is the critical thing, the real part of a complex exponential. Because once you assume things are complex exponentials, the calculations of the transfer function get very, very easy. So, we assumed it was a complex exponential. We derived a relationship between the complex amplitude of the input and the complex amplitude of the output by using voltage divider. Very simple calculations. And this we're going to concentrate on. This is the transfer function. But in any case, now that we knew what the complex amplitude of the output was, it was very easy to find out what the actual waveform in time is, because we simply put it into the real part formula. Because we use real part here, we're going to use real part calculations down there, and we discovered that the output was given by this rather complicated looking expression, but we're going to figure out what it's really telling us in just a second. One critical thing we had to do in order to derive this result was we had to convert this expression for the transfer function into polar form. And it turns out that's the way we think about transfer functions, not in Cartesian form, but in polar form. So here it is. I've written h of f in terms of its magnitude, which is the quantity here, and in terms of a phase, which is given by this. And those are the pieces that fit in here. And a little subtle detail here is that here we assume the frequency was f0, and f0 occurs down in the expressions for the final output. I now want to think about the transfer function as a general function of f, as a function of frequency. That's going to be the key insight into what the circuit is doing. And so you'll notice the notation will change. So, here's that formula for the transfer function in polar form for this circuit, and I'm going to plot it. So, this is what it looks like. We plot the magnitude and phase. Usually they're plotted one on top of the other. There's the magnitude, there's the angle, so you can compare what's happening to the phase and the magnitude at some given frequency. Okay, so let's look at this. The general rule of exploring these transfer functions to look at what happens at very low frequencies as f is going to 0, and at very high frequencies as f is going to infinity. So, at 0 frequency, this is an easy calculation. It turns out has a value of 1. Okay. As f gets very big, I mean this term is a whole lot bigger than that, because of the square root, the magnitude is falling down like 1 over f, going down like 1 over frequency. Okay. And in between, it's a nice smooth curve, getting between those two extremes of a constant and behaving like 1 over f. The phase is simply an arctangent function with a minus sign. So this is the arctangent function, very simple. It's heading toward minus pi over 2 as frequency gets big, and it's 0 at the origin. Okay, there's something to notice here. I'm plotting this as a function of both positive frequency and negative frequency. As we saw in previous videos, it turns out sines and cosines actually consist of two complex exponential terms, one with a plus sign and one with a minus sign. So negative frequency certainly exists, and you should plot your magnitude and phase as a realize that there are both positive and negative frequency components. However, it turns out there's a pretty easy thing to see in this example, and it's going to happen in general. And that is, for the magnitude, it's a symmetric function about the origin, having what we call even symmetry. And what that means is that the magnitude of h of f is equal to the magnitude of h of f of minus f. That's called even symmetry. And all magnitudes of transfer functions, of circuits and general systems have this property. So you can just tell me what the positive axis looks like, and I can plot for you what happens at negative frequency very easily. It's a mirror image, so it's a very easy thing to do. The phase has very similar kind of symmetries, and it has what's called odd symmetry, and that is that the angle of h of f is equal to the negative of the angle of h of minus f. And that's always true. So again, if I tell you what happens at over the positive frequency axis, it has negative symmetry in that the odd symmetry, negative symmetry in that this part is going to be the negative of what it is over here. So again, I give you the positive frequency part for both the magnitude and the phase. You can fill in what happens at negative frequency quite easily. I should mention that this is the magnitude being even and the phase being odd is a way of talking about what's called conjugate symmetry, and that h of f is equal to h conjugate of minus f. Turns out another way of thinking about even symmetry for the magnitude, odd symmetry for the phase, is that h of f equals h conjugate of minus f. When I write that again to make it very clear, conjugate symmetry means that h of f is equal to the conjugate of what is happening at negative frequency. So all transfer functions have this property, so it makes it very easy to do your plotting and everything else. Well, okay. Well, what is this curve telling us? Particularly the magnitude. So, as frequency increases, the output voltage, V out, will be getting smaller and smaller and smaller. So what I'm assuming is that the input voltage, the amplitude of our sine wave, is a constant across all frequency. And as I change the frequency of that input, the output, just because of the action of the circuit, is going to get smaller and smaller and smaller. Okay? That's what we call a low-pass filter. And I'm going to give you the reason for the word filter here in just a second. But low pass, I think, is pretty straightforward. It's passing through, letting through things in the low frequency range, and things at higher frequency ranges tend to be suppressed. And we're going to see how that happens for a very simple example here. Suppose our input voltage consisted of a sum of two sinusoids, F1 and F2, and you can see I've allowed them to have general amplitudes. What's the output going to be when the input consists of a sum of two sinusoids? Well, we're going to use the principle of superposition, of course, because the circuits are linear. So, when you have the input is equal to the first sinusoid, we know what the output is. When the input is equal to just the second sinusoid, we know what the output is. And when the input consists of the sum of those two, superposition applies, and you just add those answers up. This is the beauty of having a linear circuit. This is the very definition of being linear. The output for a sum is equal to the sum of the outputs. Okay, so what's happening here? Let's assume that F1 is down here somewhere, and let's assume that F2 is out here somewhere. So let's assume, for sake of argument, that the amplitudes of these are about the same. But what's going to happen on the output side is that the transfer function at F2 is much smaller than it is at frequency F1. So this term is going to be attenuated. Filtered is the term. It's going to tend to filter out the high frequency term. So the terminology is that the low frequency area, the frequency region over which things get through, is called the pass band. The band of frequencies over which signals pass through, and for frequencies that are much higher, you're in what's called the stop band. The circuit, the filter, tends to stop that from coming out. So this again is a low pass because it's in the low frequency regions that get passed through, and the high frequencies tend to be attenuated. So so what's high and what's low? Well, you can see this curve is very gradual, and it's not as if there was a clear delineation between the two. An ideal low pass would have a frequency characteristic that looks like this. So let's say it has a gain of 1 at low frequencies, and then it instantly boom, jumps down and at some frequency goes to 0. That would be what we call an ideal low pass. Well, the RC filter we have certainly doesn't have that characteristic, but we can think about it by defining what's called a cutoff frequency. So the cutoff frequency is generally defined to be the frequency at which the magnitude at that frequency is 1 over the square root of 2 times the maximum value of the magnitude, wherever that occurred in frequency. So for a low pass, this maximum is occurring at the origin, has a maximum of 1, and you change frequency till the output is equal to 1 over the square root of 2 of the value at the origin, which here is 1. And why 1 over the square root of 2, you might be asking. Would you think about that for a second? What could be so important about the 1 over the square root of 2? And the answer is power. So at this frequency, because power is proportional to signal squared, the power of the sinusoid at this cutoff frequency will be 1/2 of the value it is at the maximum. So at this cutoff frequency, the power in the output will be 1/2 of what it was at the origin. If you go to higher frequencies, the power output gets less and less and less and less at those frequencies. So for our RC low pass, we need to look at the formula to figure out where the cutoff frequency is. And it's pretty easy in this case, because we know at f equals 0, the value is 1, and the frequency at which this square root is going to be 2 is when this term equals 1. And so solving for that, we get that the cutoff frequency is equal to 1 over 2 pi times r times c. So when it comes to designing a circuit, suppose you wanted to design a filter that would pass, have a cutoff frequency of 1 kilohertz. Well, what you'd do is set this equal to 1,000, and what you'd find is that the only thing that you need is for the product of R and C to be over 2 pi. So the important point here is that it's the product of the component values. We've seen this before. The only thing you need is the product to have certain properties, so you can choose the resistor and capacitor separately according to whatever criteria you want, but the product of the two is what determines the cutoff frequency, not the individual component values. It gives you some latitude in doing the design, it turns out. Okay, so it turns out there are more kinds of filters out there other than low pass. So the low pass we've talked about. So generically, I'm only going to draw the positive frequency axis because we know what's going to happen. For the magnitude, generally they look something like that. That's a generic low pass which has a cutoff frequency somewhere there, where this value here is 1 over the square root of 2 times whatever the value is at zero frequency. You can also have a high-pass filter. And high-pass, what it looks like is pretty easy to see. Where the name comes from, tends to suppress low frequencies, let through the higher frequencies, and its cutoff frequency would be somewhere here. And that value is 1 over the square root of 2 times whatever the value is at infinite frequency. And then finally, there's the bandpass filter, which what this means is that it passes a range of frequencies and suppresses the other ones. So if we plotted it, tends to look something like that. And this means it has 2 cutoff frequencies, a lower cutoff frequency and an upper cutoff frequency. We refer to the width, the distance between the 2 cutoff frequencies, as being the bandwidth of the filter. And that's an important parameter when you start talking about bandpass filters. Sometimes we refer to the upper and lower cutoff frequencies. Other times we might refer to the center of the band and the bandwidth as specifying the bandpass filter, whichever way seems most convenient. We're going to discover as we go through this course that all these filters have very important uses and occur very frequently in real-world applications. Okay, I want to explore what really happens when you build a RC low pass. Because you can see I'm going to use specific element values. I really constructed this circuit. The input is going to be a sine wave. And we know that from all we've done that the output for a general filter is going to be the transfer function, magnitude of the transfer function times the sine, plus the sine wave with a given that has a phase shift given by the filter. And we have calculated this for the RC low pass several times, and we know that what it's going to do is the magnitude is given by this expression and the phase is given by this. Okay, so first thing we want to do is calculate exactly where the cutoff frequency is going to be. To do that, you need to find out where the magnitude is its maximum value, and it's pretty clear from this expression that the maximum value occurs at a frequency of 0. This is, after all, a low-pass filter. And then we want to see where the magnitude is 1 over the square root of 2 times that maximum value, which in this case is 1. So it's pretty clear that it's going to be equal to 1 over the square root of 2 when this expression equals 1, because we have the square root of 1 plus 1 will give us what we want. So we've calculated this several times, and we know that the answer is that the cutoff frequency is given by 1 over 2 pi RC. And when you stick in the explicit values for our circuit element values, we have 10 to the 4th for the resistor, and this is 220 nanofarads. Like I said, you don't usually have very large valued capacitors in circuits. So, and we get 72.34 hertz. We'll have to see if that really works, really happens when we look at the output of the circuit that has these circuit element values. When you plot this, some things I want to note before we go to the simulation. We predict the cutoff frequency is going to be 72.34, which is a frequency somewhere like this. I want to point out something that's a special thing for this RC low pass. Where is the phase? What is the phase at the cutoff frequency? Well, when the frequency is equal to 1 over 2 pi RC, this expression is 1. The arctangent of 1 is pi over 4, 45 degrees. So the phase will be minus 45 at that point. Okay. So here's what we should expect. When you have frequencies less than Fc, the amplitude of the output should be going up until it gets to very low frequencies. It should be about the same as the input. The phase shift will become smaller and smaller and smaller, and again, as you go towards 0 in frequency, the output in terms of its phase shift will also look like the input. On the other hand, if you go way beyond the cutoff frequency, the amplitude of the output will be going down and down and down and down, and the phase shift is headed toward minus 90 degrees, minus pi over 2. So, what is sine of 2 pi ft minus pi over 2? What does that equal? And what I get is that that is minus cosine. Okay, so that's what we should expect. As the frequency gets very high, amplitude gets smaller and smaller and smaller, and the phase is going, the output is going to look more and more like a minus cosine when all is said and done. Well, let's see if that really happens. So here's my input. The frequency is, here's the frequency generator. It's setting up a sine. This output number here is the peak-to-peak amplitude of the output. Well, 80 hertz is a little bit above the cutoff frequency, so the amplitude should be 1.414. If we were at the cutoff frequency, it's a little lower than that because we're too high in frequency. I've lowered it to 74.5, getting closer to 1.414, but it's not quite correct. I put in 732. It's getting closer, and for this oscilloscope, we could have typed it in all the time. So we point out that the white line is the input to our circuit. The red line is the output. So you can see the amplitude is down by some amount, and this is telling me exactly what it is. All right. Well, let's explore what happens as I go to a lower frequency. So I got to change what's called the time base of my oscilloscope. I'm going to make it go down by a factor of 10 in frequency. We're now at 7.3 hertz. And as you can see, the red line, the output, is almost the same as the white line, the input to the filter. and it's got very little phase shift, and that's exactly what we should predict. Let's go back to 73 hertz, and we can see, yeah, the amplitude's gone down like it should. Now I'm going to set it up to go up to a very high frequency. And you can see the output is greatly attenuated. And if you look carefully at that waveform, looks to me like it looks like a minus cosine to me. So all the theoretical predictions are correct. Now what I'm going to do is go back to our original setting, original frequency, and I'm going to vary it continuously now so we can see the go up in frequency, so the amplitude will be going down as the frequency goes up, just as predicted. The phase shift keeps increasing, getting more negative. And then if we go back the other way, we see the amplitude go up and keep going down, down, down in frequency below the cutoff frequency now, well inside, looks more and more like the input. Okay, so let's talk about the big picture. We're going to make sure we really understand what's been happening here. We started with the circuit. We assumed complex exponential input, which meant that every voltage and every current in the circuit was also a complex exponential. Based on that notion, we defined impedance and converted the circuit to being an equivalent circuit, so far as complex amplitudes are concerned, so that we had impedances representing the circuit elements. Because of this assuming complex exponential inputs, we can now use all the shortcuts that we developed for resistor circuits, and this makes the calculations quite easy. And I think it'd be pretty obvious that the Meyer-Norton and Thevenin equivalents follow just as well. So since they were based simply on using the series and parallel rules and even a bit more generally, the Thevenin equivalent, when you have impedances, is exactly the same, except this is now an impedance and this is a complex amplitude. So the frequency of the source is implicit. All we care about in representing a circuit with a Thevenin equivalent are the equivalent source and the equivalent impedance. And the Meyer-Norton has exactly the same properties we derived before. The two impedances are the same, and that's the amplitude of a current source, and that same formula applies for that we derived, but for impedances. That the equivalent the amplitudes of the equivalent circuit obey this relationship that's the equivalent impedance. So there's no real surprise there, and you can now use these equivalents in RLC circuits just like we did for resistor circuits. Okay, well, there's something else that becomes very easy to talk about when you have complex exponential or sinusoidal sources. So again, I'm going to think about all my circuit elements as being an impedance with some complex amplitude for the voltage and a complex amplitude for the current going in. And now what I do is a power calculation. So I'm going to do this in general. I'm going to assume that the complex amplitudes have a magnitude and a phase for both the current and the voltage. Okay, which means that speaking about them back as time domain quantities, there's the magnitude there's the magnitude for the voltage, and there's that phase shift. So I'm thinking about my little v of t as being the real part of this, and for I of t you take the real part of that. There you go. Well, we know what power is. Power is always voltage times current. Well, I could plug in these two formulas into here and try to simplify it. Turns out there's a much easier way, which I'm going to show you, which actually brings up a very interesting point. So I'm going to do that calculation in a slightly different way. What I want to do is use Euler's formula. So in addition to, we can explicitly write out the real part, if you will, formula as being just Euler's formula. We've seen how this works before. Now is what I want to do is I want to plug that in. I want to plug these expressions in to that product. Well, it's very easy to multiply this out, and it turns out it really simplifies the calculations a lot. So the way to think about this is that the voltage is now a sum, the current is now a sum. So when you multiply the two together, you get all four possible cross products. This times this times that, that times that, and that times that. So if you multiply them out, you'll notice that some terms, the complex exponential part cancels, and for other terms, the complex exponential adds. And when everything is said and done, this is the expression that you get. Well, this is quite interesting. Now, if you look at these two, for example, this is the complex conjugate of that. All right, because the conjugate of a product is the product of the conjugate. V conjugate, V, the conjugate of V is V conjugate, and the conjugate of I conjugate is just I. Get it back again. Same thing happens out here. This is the conjugate of that. So those are real parts. And notice, because you multiply by a quarter, you have to put a half factor in to get the real part in the final answer. So what does this say about the power when you, this is the actual power. There's nothing complex here at all. Those are actual power values. P of t is equal to some number. And then you get a term that turns out to have a frequency which is at twice the frequency of the source. So if you plot this term is a constant. It's a function of time now. And rippling around it somehow is the time-varying part. Well, we know that energy is the integral of power, so the time-varying part really doesn't contribute over the long term to energy consumption. Sometimes it goes to zero, when this term goes, this plus this goes to zero, and sometimes it goes positive. The only thing that contributes long term is that term, and that's called the average power. This is a general result for all RLC circuits in which the source is a exponential, is a sinusoid, which we think of as a complex exponential. So average power that is consumed is given by the real part, half the real part of VI conjugate, where these are the complex amplitudes of the circuit element we're worrying about the power consumption for. So this is what is known as complex power. So in general, the only thing that's really important is the p-half term. Is the p-half, which is the real part of complex power. And whenever we have an impedance, it turns out this formula for complex power can be rewritten in terms of impedance. So just plugging in the relationship for impedance into VI conjugate formula, you can write it either as Z times the magnitude of the current squared, or 1 over the impedance times the magnitude of the voltage squared. I'm going to stick with this one because it looks a little bit simpler. And let's see what it looks like for all the three common circuit elements. And certainly we've seen this before, but for the resistor, the power is just 1/2 R times the magnitude of the current squared, and there is no imaginary part, so the real part of that is just what you got. Again, stating it's resistors that dissipate power. For the capacitor, though, the impedance is complex, is imaginary valued, rather. So that means when you take the real part, you get 0. Again, this is saying that the capacitors, as well as the inductors, do not dissipate power. And what they contribute to is that time-varying part, that part where the power consumption goes up and down. So sometimes they consume power, sometimes they get it back in certain times, but in the long term, they don't consume or produce power when you have a sinusoidal input. Okay, so in summary, by thinking of each element as a complex valued resistor, what we've called an impedance, we get a general picture of what circuits do and how they behave. We can use, to solve those circuits, we can use the series and parallel rules, voltage divider, current divider. We can use the equivalent circuits. We can talk about transfer functions and filters. These are going to be very important concepts coming up. Transfer functions are going to occur all the time. Filtering, thinking about transfer functions is what kind of categorize them according to what kind of filter they are. You have to plot the transfer function and see how it works out. We can also talk about power by using just the complex amplitudes. We don't have to really go back, solve for what the little v and little I are, and then multiply them out and get it. We have a very general formula just from using the complex amplitudes. Now, I do want to point out, it's very important that these results only apply when the source is a sinusoid. Remember, what we did was assume that the source was the real part of something that looked like a complex exponential. And so all these formulas apply only when we have a sinusoidal input. When it's a sum of sinusoids, superposition applies, and we know how to solve that. Well, you might be wondering, what happens if it's not a sinusoid? For example, suppose it's a pulse or a square wave, those other signals we've been talking about. Have we gone down a blind alley? Is this going to go anywhere? Well, as you might think, this is not the end of the story. We can talk about very general source waveforms other than sinusoids. Turns out these are the building blocks that we're going to use later in the course.